A 0.1 moles per cubic decimeter solution of a weak acid HA was prepared by diluting an appropriate amount of the pure weak acid to 25 cubic centimeters with distilled water in a volumetric flask at 25 degrees Celsius. The pH of this solution was 3. Question number 1. Considering the equation, calculate the dissociation constant Ka of the weak acid. The equation for the dissociation of this weak acid was given in the question, and we have to calculate the dissociation constant Ka of this weak acid. This dilute HA solution was prepared by adding distilled water to an appropriate amount of this pure weak acid. Then final concentration of this weak acid HA is 0.1 moles per cubic decimeter and the volume is 25 cubic centimeters. We need to calculate the dissociation constant Ka of this weak acid. Now we will move to the calculation. Initial concentration of the weak acid is 0.1 moles per cubic decimeter. As this is a weak acid, it undergoes partial dissociation. Now check the stoichiometry in the given equation. So we can see the stoichiometry is 1:1. Therefore, if X amount is dissociated from the weak acid, the produced amount of H3O plus as well as A minus are X. So we can write plus X and plus X for both H3O plus and A minus. Next, concentrations at equilibrium. HA 0.1 minus X, H3O plus X, A minus also X. The dissociation of a weak acid is very low. Therefore, we can assume the initial concentration is very much greater than the dissociate concentration or the dissociate amount. The reason is HA is a weak acid. Usually, weak acids undergo partial dissociation and the dissociated amounts are very less compared to the initial amounts or the initial concentration. Therefore, we can assume 0.1 minus X is almost same as 0.1. At equilibrium, concentration of H3O plus is the same as the concentration of A minus. Now, we will write the Ka expression for this weak acid. Ka equals concentration of H3O plus into concentration of A minus divided by the concentration of the weak acid HA. Now the concentration of H3O plus and the concentration of A minus are the same. Therefore, we can write H3O plus concentration power 2 divided by the concentration of the weak acid. To calculate the value of Ka, we need the concentration of H3O plus at equilibrium as well as the concentration of the weak acid. Concentration of HA at equilibrium is the same as its initial concentration because the dissociation of weak acids are very low. The concentration of H3O plus at equilibrium can be calculated using the given pH value. At equilibrium, pH value of this dilute HA solution is 3. Therefore, H3O plus concentration at equilibrium is 1 into 10 to the power minus 3 moles per cubic decimeter. Now, we know the concentration of H3O plus at equilibrium as well as concentration of the weak acid at equilibrium. Therefore, by substituting values for this equation, we can find the value of Ka. Ka equals concentration of H3O plus 1 into 10 to the power minus 3 moles per cubic decimeter to the power 2 divided by the concentration of HA 0.1 moles per cubic decimeter. Ka equals 1 into 10 to the power minus 5 moles per cubic decimeter. Question number 2. A dilute solution of this weak acid HA was titrated with a strong base BOH. It was found that the pH of the titration mixture after reaching the equivalence point was 9. Calculate the concentration of the salt AB in the titration mixture. At 25 degrees Celsius, Kw is 1 into 10 to the power minus 14. This is a strong base weak acid titration. The neutralization reactions between weak acids and strong bases produces weakly basic salts. According to the given question, HA reacts with BOH to produce this basic salt AB. Now we will move to this equivalence point. Equivalence point is the point at which stoichiometric amounts of these reactants are exactly reacted. Therefore, what we can find at the equivalence point is the salt AB. There is no remaining HA or the added BOH in the reaction mixture at the equivalence point. And the pH at the equivalence point is only due to the presence of this basic salt. pH value at the equivalence point is given as 9. Therefore, POH at the equivalence point, it's 14 minus 9. POH is 5. That means OH minus concentration at the equivalence point is 1 into 10 to the power minus 5 moles per cubic decimeter. At the equivalence point, a basic salt is present and these OH minus ions are produced from the basic salt AB. We have to calculate the concentration of the salt AB at the equivalence point. Now we will move to the calculation part. The salt AB, which is a strong electrolyte, completely dissociates into its ions. The anion A minus comes from the weak acid and the cation B plus comes from the strong base. These anions of weak acids, which are known as conjugate bases, undergo hydrolysis reactions and produce the respective weak acids and OH minus ions in the solution. Now, we will write this hydrolysis reaction for the conjugate base of HA or the hydrolysis reaction of A minus. But this theory is not applicable for these cations or anions derived from the strong acids or strong bases. If the concentration of AB or the salt is C moles per cubic decimeter, according to the stoichiometry, concentration of A minus as well as concentration of B plus is C. Initial concentration of A minus is C moles per cubic decimeter. If the hydrolyzed amount of A minus is Y, the produced amount of HA as well as OH minus are also Y. At equilibrium, concentration of the conjugate base is C minus Y and the produced amount of both HA and OH minus are Y moles per cubic decimeter. This conjugate base A minus is a weak base. Concentration C is very much greater than the dissociation Y. Therefore, C minus Y is almost the same as C. Concentration of HA and the concentration of OH minus produced at equilibrium is the same. Now, we will write the Kb expression for this conjugate base. Kb equals concentration of HA into concentration of OH minus divided by the concentration of this conjugate base A minus. The concentration of HA and OH minus are the same. Therefore, we can write concentration of OH minus to the power 2 divided by the concentration of A minus. The dissociation constant of this conjugate base is not given. But during the first question, we have calculated the dissociation constant or Ka of this weak acid Ha. There's an equation which relates the dissociation constant Ka of the weak acid and the dissociation constant Kb of the conjugate base. Ka into Kb equals Kw. This expression can be used for any conjugate acid-base pair. Kb is Kw divided by Ka equals OH minus concentration power 2 divided by A minus concentration. A minus concentration equals OH minus concentration to the power 2 multiplied by Ka divided by Kw. Now, substitute values for this equation. Hydroxide concentration is 1 into 10 to the power minus 5 moles per cubic decimeter. We have calculated the OH minus concentration from the given pH value. Then, the value of Ka we have calculated during the first question. It's 1 into 10 to the power minus 5 moles per cubic decimeter. Kw 1 into 10 to the power minus 14 mol squared dm minus 6. A minus concentration is 0.1 moles per cubic decimeter. Therefore, the concentration of the salt AB also the same 0.1 moles per cubic decimeter. This is the answer for question number 2. Question number 3. The above titration mixture was diluted 100 times by adding distilled water. Calculate the pH of the diluted titration mixture. The above titration mixture is the previous salt solution and the concentration we have calculated during the question number 2. It is 0.1 moles per cubic decimeter. Now, it is 100 times dilution. That means if the initial volume is V, the new volume is 100 V. And we need to calculate the concentration of this diluted salt solution. We can use the equation C1V1 equals C2V2 for these types of systems. Initial concentration is 0.1 moles per cubic decimeter. Initial volume is V. New concentration we use as C2. The new volume is 100 V. C2 is 0.1 divided by 100, 1 into 10 to the power minus 3 moles per cubic decimeter. Now, we have calculated the concentration of this diluted solution. That means concentration of the conjugate base A minus in this diluted solution is also the same, 1 into 10 to the power minus 3 moles per cubic decimeter. Earlier, we have derived an equation which relates the concentration of A minus, concentration of OH minus, Kw and Ka. We can use the same equation to get the concentration of OH minus after dilution. OH minus concentration equals the square root of Kw divided by Ka into A minus concentration. Substitute values for this equation. Kw 1 into 10 to the power minus 14 mol square dm minus 6. Ka 1 into 10 to the power minus 5 moles per cubic decimeter. A minus concentration in the diluted solution 1 into 10 to the power minus 3 moles per cubic decimeter. Therefore, OH minus concentration is 1 into 10 to the power minus 6 moles per cubic decimeter. pOH is 6. pH equals 14 minus 6. Therefore, pH of this diluted salt solution is 8. This is the answer for the question number 3.